In a previous lesson, we saw if x equals x0 is an ordinary point of the types of differential equations that we're looking at, then we can always find two linearly independent solutions in the form of a power series. In this lesson, we saw if x equals x0 is a regular singular point, then we have at least one solution that's in the form of a power series. It turns out if R1 and R2, the indicial roots, differ by an integer, then we can use R1 to find Y1 and then reduction of order to find R2. We're going to start our work finding the indicial roots. And remember, for finding our indicial roots, we want the first term to be x squared y double prime. So we need to multiply everything by x squared. We get x squared y double prime plus 3xy prime minus 2x squared y is equal to 0. And remember that Cauchy-Euler-esque form, we see 3xy prime, and anything besides xy prime is lowercase p of x. So lowercase p of x is equal to 3 in this case. And in the term negative 2x squared y, we have the lowercase q of x is equal to negative 2x squared. Remember, we had a constant a sub 0, which is the constant term of lowercase p of x, and so in this case, a sub 0 is equal to 3. And we had that b sub 0 was the constant term in lowercase q of x, but since q of x is negative 2x squared, b sub 0 is equal to 0. We can then write down our indicial equation, which is r times r minus 1 plus 3r is equal to 0, giving us r squared plus 2r is equal to 0, and indicial roots of r equals negative 2 or 0. We'll note that they differ by an integer and set that aside for now, looking for confirmation when we do our sigma process, which we're going to do on the original equation. We don't need to do it on the beefed up equation that we created. For y double prime, we have the sum as n goes from 0 to infinity of n plus r times n plus r minus 1 c sub n x to the n plus r minus 2. Where we see this plus 3 over x y prime, instead of multiplying by x, we're dividing by x. So instead of adding to the exponent as we keep doing, we're going to subtract from it. That's going to give us the sum as n goes from 0 to infinity of 3 n plus r c sub n x to the n plus r minus 2. Continuing with the equation, we have minus 2y is equal to 0, so minus the sum as n goes from 0 to infinity to c sub n x to the n plus r is equal to 0. Notice that the first two sigma expressions have the same starting value for the index and the same exponent on the variable. We're going to go ahead and combine those two sigma expressions. And if you look at the exponent n plus r minus 2 on those first two sigma expressions, if I wanted to make that look like a k plus r, then I'd need to add 2 to that, subtract 2 from the starting value of the index. K would start at negative 2, so I'm not going to do that. That means k plus r minus 2 is going to be the exponent. So the first two sigmas, when I combine them, are going to just change n to k's, and we'll move on from there. In the sigma expression for y, we're going to replace n plus r using k plus r minus 2, and then the starting value for the index is going to increase by 2. Here's the result. The sum as k goes from 0 to infinity, notice we have n plus r in both of those first two sigmas. We're changing n's to k's, so I'm going to factor that out and write down k plus r. From the first sigma, we have k plus r minus 1, but from the second sigma, we have plus 3 after we factor out n plus r. That's going to give us a factor of k plus r plus 2 times c sub k x to the k plus r minus 2, and move on. For the the third sigma expression for y, we're going to start this at k equals 2. It goes to infinity, 2 c sub k minus 2 x to the k plus r minus 2. All that is equal to 0. Having made the exponents match, we're now going to make the indices match. For us, that means we're going to write down the k equals 0 term and the k equals 1 term. For the k equals 0 term, we have r times r plus 2 c sub 0 is equal to 0, neglecting the x's because that doesn't factor in what we're doing right now. For k equals 1, we've got r plus 1 times r plus 3 c sub 1 is equal to 0. We saw in a previous video that we use the term that has x with the smallest exponent to find our indicial roots. That term is going to happen when k is equal to 0. Therefore, r times r plus 2 is equal to 0, giving us indicial roots of r equals 0 or negative 2, which agrees exactly with what we saw above. For the second equation we have here, since r is equal to 0 or negative 2, we already have those values for r. For that product times c1 to equal 0, it must be the case that c1 is equal to 0. That'll happen every time the starting value for the index at this point differ by 2. Now we can skip ahead to forming our recurrence relations. From the first sigma expression, we have k plus r times k plus r plus 2 times c sub k. From the second sigma expression, we have minus 2 c sub k minus 2, and all that's equal to 0. For k starting at 2, 3, 4, etc., had we combined the sigma expressions. Solving for the constant that has the highest subscript, we get c sub k is equal to 2 over k plus r times k plus r plus 2 c sub k minus 2. Again, that's for values of k starting 2, 3, 4, etc. Our indicial roots are 0 and negative 2. And using r equals 0, we get that c sub k is equal to 2 over k times k plus 2 c sub k minus 2. Using r equals negative 2, we get c sub k is equal to 2 over k times k minus 2. Folks, we have a problem here. K is supposed to start at 2. If I put k equals 2 into a denominator, k equals negative 2, we get an undefined expression. Those are going to be no good to us. So we're going to do our work exclusively for the r equals 0 indicial root. Doing so will give us, for k equals 2, c sub 2 is equal to 1/4 c sub 0, and for k equals 3, c sub 3 is equal to 2/15 c1, but remember c1 is 0, so that thing equals 0, and we need now k equals 4. That's going to give us c4 is equal to 1/48 c sub 0 after we do our substituting. For y sub 1 then, we get what we would write as c0 plus c1x plus c2x squared and so on. We're going to factor out the c0s, so we're not going to write those. And remember that we found earlier that c1 is equal to 0. So y sub 1 is equal to 1 plus 1/4 x squared, right? C2 is associated with the x squared term, plus 1/48 x to the fourth, c4 is associated with the x to the fourth term, plus ... That's the only solution we're going to get from this process. And this is what we kind of expected here at some point. There is at least one solution of the form of a power series. Well, we've got the at least one. And in general, I'll say when the indicial roots differ by an integer, one of a couple things is likely to happen. One of them is you're going to end up with some undefined expression and you're going to have to stop with that indicial root. Another thing that could happen is nothing's undefined and you crank out constants and you find that the coefficients that you get end up repeating what you got using the other indicial root. So it just becomes redundant and you don't have two separate series. At this point, recall reduction of order. For an equation in standard form, y double prime plus p of x y prime plus q of x y, these are the uppercase P and uppercase Q that we've used most of the course. Given a solution y1, we get y2 using the formula y1 times the integral of e to the negative integral of p of x dx divided by y1 squared times dx. Our original equation was in standard form, and we see that uppercase p of x is equal to 3 over x. So, since p of x is equal to 3 over x, we have that the negative integral of p of x dx is equal to negative of the integral of 3 over x dx, which is negative 3 times the natural log of x. Making that the exponent on e, and using the property of exponents that says that the coefficient of a log becomes the exponent on the argument, we find that e to the negative integral p of x dx in this case turns out to be 1 over x cubed. That's going to take the place of the numerator in the reduction of order formula. For the denominator, y1 squared, our y1 is an infinite series. So to write this down, we would have y2 is equal to y1 times the integral of 1 over x cubed times 1 plus 1/4 x squared plus 1 over 48x to the 4th, and so on. Oh, that's squared down there. That power series is squared. Okay, this is not something that I would be willing to do by hand. My tool of choice here is wolframalpha.com. I tried putting this into wolframalpha.com all at once, well, just the integral all at once, and it didn't really work. I don't want to say I broke Wolfram Alpha, but it didn't really work. So what I did was I put the quantity squared term, just with a few terms inside of it for y1 squared, into Wolfram Alpha. That was step 1. And then I multiplied that result by x cubed. And then I told it, find the reciprocal of all of that. And then I asked it, now go ahead and integrate that. I'll show you what that looks like. I've got Wolfram Alpha here, and I've put 1 plus 1/4 x squared plus 1 over 48x to the 4th quantity squared into it. The first thing it does is it repeats your input, so it makes sure that what you thought you put in is what you put in. I'm going to go down here to where it says expanded form, and then if you hover over this on a computer or tap it on your tablet and go to plain text, you can copy the plain text. You just tap on where it says copyable plain text. And then back up here to the bar. Remember, we need to multiply x cubed times all of that. So I'm going to paste from what we just copied. I see I need some parentheses in here, so let me make that happen. I'm again going to go down to the expanded form and go for the copyable text. I'm going to copy that, paste it up here, but we need the reciprocal of that. So I'm going to divide 1 divided by all that stuff that we just pasted. The first result isn't really useful for us. I'm not sure Wolfram Alpha is going to be okay integrating that 1 over a bunch of the sum of a bunch of fractions. But if we keep scrolling down, we'll see series expansion at x equals 0. That's the one I want. I'm going to copy that. And this time what we want to do is integrate. I'm going to paste this, but I got to delete Lorentz series. We don't need that information. And we also need to delete the plus O x over 2. That's just referring to big O notation. If you know what it is, cool. If not, don't worry about it. And then ask it to integrate. When I do that, I get an output that I can understand here. So we can see that y2 is equal to y1 times 7 over 96x squared minus 1/2, I guess 1 over 2x squared, minus 1/2 natural log of x. That logx in Wolfram Alpha is the natural log of x. I'll put plus ... because that is an infinite series. And then this is the rest of the story on what Frobenius told us, which is basically we have at least one power series solution. And if we can only get one power series solution, then the other solution is going to contain a natural log. Since the solution that we get using this process is fairly cumbersome, what I'm going to do is just remind us we wrote down what y1 is. It would be good form to go ahead and bring that down here. We have what y2 is, and it references y1. And then I'll just close this out by saying y, the general solution, is c1y1 plus c2y2.